Good afternoon, everyone, or morning if you're doing it in the morning. I'm going to go through what we're actually doing with growth and decay today. As you can see, it's another one in our increase and decrease percentages set of lessons, and it extends what we looked at last time. So if you've had your feedback from last lesson and you still didn't really get that, it's a good idea to go back and look at it again. So when we talk about growth and decay in maths, we're talking about exponential growth and decay. If something grows exponentially, it means that we're multiplying it each time rather than just adding it on. If you think about a sequence, it would be like a geometric sequence, say 3, 9, 27, and so on, where you're multiplying by 3 each time, rather than a linear sequence, which is say 2, 4, 6, 8, 10, where you're adding each time. So we're multiplying each time, and when we're talking about the rate that it increases or decreases with something with the growth and decay, it's the growth ratio. When we looked at geometric sequences, we called it a common ratio. And it's what we use with multipliers. When we increased something by 10%, the growth ratio would have been 1.1 because we're increasing it by 10%. 1.1 is our multiplier for 10%. Now, when it's being multiplied, this could make it bigger if the growth ratio is more than 1. And then we call that growth, but it could make it smaller, decay, if it's less than 1. That's what we looked at with depreciation. So we talked about growth with compound interest and decay with depreciation. That's what we're going to begin looking at today before we extend some of our ideas. Now, last lesson we looked at it when the percentage change stayed constant, stayed the same, and that's not always the case. In real life, interest rates, for example, can change with your bank account. So, for example, the example below, Jimmy and Magda want to open a children's account for their son, and they see these two advertised. Bank 2 is 1% interest paid all the time. Bank 1 is an introductory rate of 2.5% for the first year. And then after the first year, it changes to 0.5%. So they get 1 year at that higher rate, and then everything else is at that slightly lower rate. And we're interested which will give them the best return on their investment. Well, if we look at each one and we say, well, let's say they invest £1,000. And the great thing with interest and with percentages and just looking at the changes is we could choose any number. 1,000's a good number to work with. 100 would be a good number to work with. You could even do something like £2.73, but that would make it a lot more challenging to work with as a set of numbers. You'd end up hitting decimals a lot more quickly. So you can see there on the left, in that yellow box on the left there, that's for Bank 1. And we can see it starts off with £1,025, whereas Bank 2 on the right here is only £1,010. Continuing on, the gap remains, so that first year the gap's about £15, the second year it's about £10, the third year it's about £5, and the fourth year, actually Bank 2 has now overtaken Bank 1. And we used a rate of 1.025 as the introductory rate on year 1, so it was times 1.25, but then when we got to year 2 and onwards, it was at 1.005, and we're using this multiplier method. We could use the method of finding the percentage and adding it on. That would work just as well. We see in Bank 2, our multiplier is just 1.01 the whole time, so we can just use our quick formula with powers. So what advice might you give to Jimmy and Magda? Well, you might say, if you're only going to keep it in there for a couple of years, actually Bank 1's probably the best idea. And if you're going to keep it in long term, Bank 2's probably there. Or you might even say, well, stick it in Bank 1 for the first year, and after that first year, move it to Bank 2, because you'll get a lot better long-term interest rate. And a lot of banks will expect you not to change from them. You'll find good introductory rates, and if you shop around, you can often get a lot more on your money than just keeping it in one place. Now, this obviously looking at an exact value. But we might want to know what it is as a percentage of the original amount. So for example here, Bank 1 in year 1, the total interest paid was 2.5% of the original amount. Not surprising, it was 2.5% rate. At the end of year 2, there was a total of £30.13 of interest, which is 3.013% of the original amount. And then we can do the same thing in year 3 and year 4, and we use our formula to calculate percentage change. It's a £30.13 increase out of £1,000. We can do the same thing with Bank 2 and look at that. But with Bank 2 there, obviously our percentages go up, and we've used our original amount, but we could do this if we didn't have an original amount. So say, for example, a virus spreads exponentially at a rate of 20% each day. What will be the percentage increase in people infected after 5 days? So it's spreading exponentially, so even though we're multiplying it, each day we'd multiply it by 1.2. If we're doing that 5 times, it would be 1.2 times 1.2 times 1.2 times 1.2, which we can just write as 1.2 to the power of 5. So essentially, for our increases, we're multiplying it by 2.48832. And we know then that's the multiplier that's used for 248.832%. This refers to an increase of 148.832%. So a 20% increase each day means that after 5 days, the number of people infected would be 148.8% more than the first day. It's roughly 2.5 times as many people. And we're seeing something like that with the coronavirus when we're looking at what we call the R number. And the R number, if it's 1, it means it's roughly staying the same each day. If it goes above 1, we'll start to see this exponential growth, which is why they're talking about it keeping it below 1 as being really important. Obviously, with that, there is that little bit where actually people will recover. Exponential growth will just tell you the total number of people that have been infected at any one point in total. Now, like I say, we often deal with exponential growth and decay with populations, and that can be of people, of animals, or even, like I just said, with disease. So question here, and this was taking into a bit more of an advanced level of what we're going to look at. The population of Knappsford in 2020 was 3,800 and is believed to be growing at a rate of 1.5% a year. We've got 2 questions there for you to have a go at. And I'll just pause for a moment. Well, you can pause it. I'm just going to go through and show you the answer. So question 1, it's very similar to what we've already usually done there. Multiplying by 1.015 as our multiplier gets us an answer of 3,914. And then to estimate the population, we'd want to use 15. And we've got this little formula here. That's our starting amount, A, the initial population. So in this case, 3,800. The growth ratio, R, 1.015. And then we're using a power of 15 because there's 15 years. So far, so much the same. Now this one, the population of a form of algae is believed to grow exponentially. Algae is that sort of green stuff that you'll see on the water there. On day 1, the population of algae was 2,240. By day 4, it had increased to 35,000. You're then asked to calculate the population of the algae by day 10. This is different. We haven't got the rate of increase. We don't know what that percentage changes each time. So we're going to have to work that out. And we can start to work out our growth ratio, our multiplier, by writing out a storyline. Day 1, there's 2,240. Day 2, it's 2,240 times R. Day 3, 2,240 times R, because each day it's being multiplied by that growth ratio, that multiplier. Notice the power of R here is 1 less than the number of days. That 2 is 1 fewer than day 3. Day 4, 2,240 R cubed. We're also told, though, that day 4 is 35,000. Therefore, we can write a formula, or an equation actually. 2,240 R cubed is equal to 35,000. We can use that to work out the value. We can start as an equation. We divide each side by, in this case, 2,240. It tells us that R cubed is 15.625. And to go from a cubed value to the value, we find the cube root. If it was R to the power of 5, we'd want the 5th root. If it was just R squared, we'd want the square root. And that tells us then that R is 2.5. So the multiplier that's being used is 2.5. So day 10, we've got 2,240 multiplied by 2.5. We're going to use power of 9. Because there's 9 days after, because it's 1 day less than day 10. That means it's been multiplied by that power, by that number, 2.5, multiplied by that 9 times. Now there's one for you to have a go at. Again, I'll give you a slight moment just to get you to find the pause button for you to have a go before I reveal the answer. Day 1, 12,000. Day 2, 12,000 R. Day 3, 12,000 R squared. So 12,000 r squared is 38,880. R squared is 3.24, and R is 1.8. And therefore, at the end of the first week, it would be 12,000 times 1.8 to the power of 6. So 408,000